Okay, so thank the organizers of this colloquium and the seminar here. It's a great pleasure to be part of it and be speaking here today. And sort of thanks for the invitation. So here's my title. I'll be talking about representations of punctured surface groups, which are also free groups, into PSLNC and a domination result there. And let me mention that this is a new result and this is early stages of a new project. So I'd be happy to have comments and feedback from this audience here. And we'll see that it has several directions that we can sort of further go. But before I get to describing what all this is about, let me give an idea of the broader context and talk of domination, some domination results, or a domination result in particular for closed surface groups. Okay, so for when your surface is a closed surface. So here's a fact as a warm-up that is familiar to sort of people studied hyperbolic geometry. It says that if you fix your genus greater than or equal to 2, exists a constant so that any hyperbolic surface of genus G has a Pans decomposition of bounded length. So each Pans curve, so I've drawn a Pans decomposition here. So this genus 2 surface, this will can be decomposed into 2 pairs of Pans, and these curves that divide the surface are these Pans curves. And each Pans curve has length less than CG. And this CG is called the Bayes constant. And this is an old result. And let me just mention the idea of the proof because it's tempting to do so. It's a very interesting and short idea. It can be expressed very briefly. And the whole idea is that a maximal disk embedded in the surface, you have a hyperbolic disk of some radius, say, that is embedded, has an area bound, okay, has area at most, at most 2 pi times 2g minus 2. So here's a pi on pi day, I suppose. Okay, and so let me try to draw such a maximal disk. It's something that maybe sort of goes and touches itself the boundary at some point, and such a distance, its area is bounded, its radius diameter has to be bounded above, and you see that you can construct a closed curve of that bounded length passing through that point where it touches itself. And that's just for one curve, and then you can have an inductive argument to do it for an entire Pans decomposition. Okay, so that's something that just to recall, and you can frame this entirely in terms of representations, slightly more algebraically. So instead of a hyperbolic surface, you can talk of a Fuchsian representation, or a discrete faithful representation of the fundamental group of a surface, which is the surface group. This is what I call a surface group. In this case, it's a closed surface, surface group into PSL2R. And length of a closed geodesic, you can also think of in terms of this element of PSL2R, this matrix, as the translation length of that matrix rho of gamma in H2. And just to kind of recall the translation length, here you can think of as the least distance removed by that element of PSL2R. So here you're varying x over H2. And this, again, you can think of it completely algebraically as in terms of the trace of the rho of gamma, or the eigenvalues of rho of gamma. So here, if rho of gamma is conjugate to this hyperbolic element, where lambda is some real number bigger than 1, translation length is just twice of log of lambda. Okay, And you can ask this question for any representation. You need not be discrete and faithful, it might be indiscrete. So you don't quite have a surface to work with anymore, but you can still talk of lengths of Pan's curves on the surface, on the topological surface, which is so elements as elements of this fundamental group of the surface group. Okay, and answer is yes, there is such a Bayes constant. In fact, for any, not just for representations of the surface group into PSL2R, but into PSL2C, where recall that PSL2C you can think of as a group of orientation preserving isometries of hyperbolic 3 space. And so you can talk of the length of gamma, the translation, as the translation length in H3. So the translation length of the element rho of gamma in H3. Okay. And this, as sort of fact is actually a consequence of a slightly more general domination result. This first domination result I'll mention in this talk is by Deroin-Tholozan. Okay, so so here's the theorem from a few years ago. It says that for any representation rho of the surface group into PSL2C. So here I'm talking of a closed surface. So it's still so this is a closed and oriented surface of genus at least 2. Of any such representation, there is a Fuchsian representation that dominates rho. So domination. So I've given one of the many equivalent definitions here, which I'll use throughout the talk. It's domination in the length spectrum, which means that for every curve gamma in the group, the rho length, or the length of gamma with respect to the representation rho is at most the length with respect to the Fuchsian representation, which is just the sort of hyperbolic length of the closed geodesic on the hyperbolic surface that this Fuchsian representation gives. Okay,
quick question.
Yes, yes.
Are you assuming discrete faithful?
No, so this is for any representation.
Okay.
Yes.
So here's the thing. So for something that's discrete faithful, this is basically the boundary of the convex hull and the associated PSL2R representation. Is that correct?
Right. So let's see. So, yes. So I mean, we'll see. What is that Fuchsian representation? So it's not a unique one. I should mention.
That's correct. Right.
So, but
right.
Yes. So I think what you're suggesting is one of the things that works. It is something that you. Okay, so I'll come to it later on. I'll come to the.
No, okay. So I mean, okay. So the thing is, I mean, this is why the reason why I wanted to ask this is basically what exactly is Fuchsian? I mean, Fuchsian means discrete by definition.
Yes, Fuchsian is discrete and faithful.
Yeah,
that's right.
Okay, so here's the thing. So suppose your original representation is indiscrete into PSL2R. That's also possible, right?
Yeah, that's also possible. Yes.
So if you have, I mean, in particular, your theorem says that if you have an indiscrete representation of, I mean, this Deroin-Tholozan theorem, basically it says that if you have an indiscrete representation into PSL2R, you can dominate it by a discrete faithful representation.
That's right. That's right. Absolutely. Okay, yes. In fact, this statement for PSL2R, I should mention, I will be mentioning later on, was already around the same time a consequence of a work of Guritod, Cassel, and Wolf. And
this is that ADS kind of thing, right?
Yes, that's right. Yeah. So they were more interested in PSL2R because it has
cross PSL.
Yes. So because it has consequences for the understanding ADS3 manifolds, but yeah. So I won't get too much into ADS in this talk, but that's certainly part of the context. Okay. All right. So yes. So this holds for any representation here. So that's sort of one interesting thing, I suppose. Let me try to kind of read rewrite this length spectrum definition of domination slightly differently, because then the next statement in the theorem would make better sense. So I can say that the supremum, as you vary over all curves in the fundamental group, in the surface group, fundamental group of the surface, that this ratio is less than or equal to 1. Okay, so this is sort of the definition of domination we are looking at. And so this is the second statement of their theorem, is that domination is strict unless rho is also Fuchsian. And this strict means strict inequality in the second formulation that I wrote down. Okay, so somehow there's it's a uniform factor by which the curves in this new Fuchsian representation are strictly greater. Okay, and this, in fact, together, these also, this implied one of the consequences is this implied a rigidity result, a famous result of Bowen. And so let me just recall that briefly, because it might be interest to this random geometry crowd here. So if an entropy of a representation, also called critical exponent in the case of discrete representations, is, you can think of it as this lim sup, as, let's say, L goes to infinity, of the log of the number of curves whose length is less than L log divided by L. Okay, so this is like a rate of growth of these curves. And so what Bowen showed is that he was looking at quasi-Fuchsian representations, which are discrete, actually. So amongst quasi-Fuchsian representations, this entropy is minimum for the Fuchsian ones. Okay, so I'm not defining what quasi-Fuchsians are, but they are the perturbations of Fuchsian representations, and they're also discrete and faithful. And it turns out that the entropy is minimum for the Fuchsian ones. And from this definition of entropy, I mean, it's automatic. I mean, once you have a length spectrum domination, like I kind of defined here. Okay, so Deroin-Tholozan's result actually implied a rigidity result of this rigidity result of Bowen. And the second remark I have is that Fuchsian representation cannot be strictly dominated by another Fuchsian representation. Here, when I talk about Fuchsian representation, I'm talking about this.
Just to,
yes.
This is also that this H of rho is also the dimension of the limit set. Is that right? Also dimension of the limit set.
Yeah, that's right. Yes. So yeah. So in fact, Bowen's statement has to do with the Hausdorff dimension of the limit set. That's how I think finally stated. But that's because this entropy is, or this critical exponent is closely related to the Hausdorff dimension of the limit set. Yes, one determines the other. So yes. And okay, so the Fuchsian representation cannot be strictly dominated by another Fuchsian representation. Here I'm talking about closed surface groups. So in other words, you can't have two hyperbolic surfaces where the lengths of all curves in one hyperbolic surface are strictly greater than the lengths in the other. This was something that was sort of observed by Thurston. And then so you have, so that's what explains the unless in the statement of Deroin-Tholozan's theorem that I mentioned. But unless it's Fuchsian already, you can strictly dominate it. Okay? So that was the result. And also finally, let me remark that they proved it in a more general context where your target is the group of isometries of any cat-1 Hadamard manifold, which is just a simply connected manifold. You can think of it as a Riemannian manifold, simply connected, and sectional curvatures are all at most -1, so it's sufficiently negatively curved. So let me give you an idea of the proof very quickly, because so this will set the context. So the idea of the proof was relied on some analysis. So you fix a hyperbolic metric, you some hyperbolic metric to begin with on the surface. You've given a representation rho, which you're trying to dominate. So you start off by considering a rho equivariant harmonic map. The existence of such a harmonic map, well, I should mention to this space X, right? So in our case, this is just H3. So in our case, H3. But the existence of such a map, in the case of H3, at least this goes back to Donaldson, and then slightly more general, that was for irreducible representations, and in slightly more general context by Labouri, and you can reduce to sort of Labouri's existence result. I don't have any assumption on rho here, notice. So there's a trick of looking at just this existence result of Labouri with slight generalization of work of Donaldson. And you start with such a harmonic map, and what you really want to choose the correct hyperbolic metric. So this is some hyperbolic metric that you started off with. You want a hyperbolic metric, G1, let's say on S, such that this, if you pass to the universal cover, you have some lift of this metric G1, and this F is one Lipschitz with respect to that hyperbolic. So it's contracting. And if you have that, then you have some kind of pointwise kind of inequality of these metric tensors. One is this pullback of the metric on X. Let's call it sort of G of X, which is this the metric in the symmetrics. This cat minus one Hadamard manifold. In this case, it's this H3 metric, the hyperbolic metric there. And you can compare it with this new hyperbolic metric G1. And there's another analytical input here that you can find such a hyperbolic metric. And this hyperbolic metric turns out to be one, so that there is a harmonic map from the hyperbolic metric we started off with to this new metric with the same Hopf differential as this harmonic map F that we had. Okay, so I mean, this is just to, in case people are familiar with some of these things. So this is the existence of such a hyperbolic metric. The fact that it's unique and exists is sort of due to Mike Wolf and independently part of Hitchin's work. And once you have this analytical input,
what's the last statement? The Hopf differential of what is equal to?
Oh, sorry, there's a typo here. I don't know what you call them. Yes. But this is F, Hopf differential. So this was a harmonic map you started off with that has a quadratic differential associated with it called the Hopf differential. And you want that to match with the Hopf differential of this harmonic map H to this target space with a hyperbolic metric.
I'm a little confused. You already have a harmonic map whose Hopf differential
with a Hopf differential F, Hopf of F, and you want a new harmonic map with the same Hopf differential, but this time you are mapping to this, it's universal cover. So you can think of it as a map between surfaces. Okay, so you have a surface to another hyperbolic surface, and that's the hyperbolic metric that works. So let me mention why. So it's sort of very briefly, this is this is where you sort of play around with a Bochner type equation for the holomorphic energy density, and you can show that the pullback of the that the metric in H3 in our case, the metric in this Hadamard manifold GX is pointwise dominated by this new hyperbolic metric that you found. Okay, so using this result of Wolf and Hitchin. Okay, so there's both of them have the same Hopf differential. They satisfy some kind of so they have a Bochner type equation for the holomorphic energy density, which was one of these coefficients identical. Okay, so that's just the coefficient of the Hopf differential. and you can play around with that and show that there is this inequality. And once you have that, then that's what gives you the one Lipschitz property of F. And
So,
with respect to this new metric now. Yes.
So here's the thing. I mean, there is some. I mean, there's some point I'm getting a little confused about. Just can you go back one slide? So basically, here, I mean, in this thing, you have a map to some abstract cat-1 space, H3 or X.
Yes.
And that gives you your Hopf differential on your domain gadget, right?
Right. Right.
Which is now S. But here, in what you are extracting out of this is a map from S tilde to. I mean, this is with the given. Sorry. This is two. So the surface that you're extracting is also to a. It's a target surface. Is that correct? This
yes.
S tilde,
right.
So
this one is the target. Yeah. So the second. So there are two kind of pieces of. Kind of
so basically,
here.
what you're doing is you're really factoring this map to H3 through a map to another surface with a different metric, so that absorbs all the Hopf differential. And from there, what is the map from? I mean, is there an induced map from S tilde G1 tilde to X?
Yeah, you can just compose. Yes, you're right. It factors through that map. Yes, that's correct. Yeah. So you're kind of what you started off with wasn't quite the the correct hyperbolic metric to look at. I mean, perhaps one can think of it that way. But then you can find the correct one, which is in fact kind of.
So essentially, you're moving in Teichmüller space according to the quadratic differential that you obtain from your abstract map to X. So you're sort of moving to a point which is closest in some sense to the map. Is
yeah, you can think of it that way.
And so what exactly is the property of the map from the target? I mean, from this modified gadget to this X, to capital X or H3. What property does it have? I mean, essentially what I'm asking is, I mean, if the Hopf differential is 0, or right? I mean, so there is no stretch, right? I mean, what property does it have? I mean, can one say something about this? I mean, essentially, see, basically, if the result of this modification is your original metric itself, that means that
so then you're what you want is this map to be one Lipschitz. Okay, so that's sort of the that's what you want out of the whole argument. I mean, so to get this bound on lengths of simple closed curves. In fact, this gives you like somewhat more like a pointwise domination of the metric tensor. So so this is what you're after. So this is this inequality that I mentioned here is what one is after. Okay, so beyond that, I mean, so I don't know how much this analytical method would tell you about the map. I mean, what to expect. I mean, so yes, if the Hopf differential is 0, by the way, that's also a minimal surface. It's not just a harmonic map. It's actually a minimal surface sitting inside, H3. But yes, I mean, anyway, we'll see a more, so the whole argument is heavy on analysis, and we'll see, things which avoid harmonic maps altogether. Okay, that's one of the things I'll talk about. Okay, so all right, so it's one of the things, let me sort of mention though, that it's crucial here for this maximum principle argument to work out that sectional curvatures of this target space X is strictly, or at most -1. Okay, so just like H3. Okay, anyway, there is a conjectured generalization in the context of PSLNC representation. So in this case, the symmetric spaces will not be cat-1 Hadamard manifolds. So you can't have the same argument, their proof. but nevertheless, they conjectured the following generalization. So let me call this space of representations to PSLNC, rep n of S. Okay, this representation variety. This is sort of, people sort of familiar with the non-abelian Hodge correspondence, which I've kind of mentioned here. This is the Petty moduli space. On the left-hand side, well, this is this non-abelian Hodge correspondence. On the left-hand side, there is the Higgs bundles moduli space. And I won't say much more about it, except that there is this space has a fibration, which I've tried to picture down below, called the Hitchin fibration over a certain vector space, which is some space of holomorphic sections of tensor powers of the canonical line bundle. On the left, you have to fix a Riemann surface structure, and you have this some kind of base space, which I've tried to picture here as this plane. And this picture is Hitchin fibration. The fibers are tori, which might be singular, like I've pictured here. And this picture has a section, there's a section of this Hitchin fibration called the Hitchin section, which is actually sort of the set of Hitchin representations, and which we'll see more of later on. Okay, so, and these intersect the tori at these points, which I've kind of marked here. And the conjecture, the more general conjecture that Deroin-Tholozan proposed, and it was fine-tuned by Song Dai and Chongling Li, is that in each fiber of this Hitchin fibration, the Hitchin representation, the place where this Hitchin section, this sort of dotted plane intersects these fibers, the Hitchin representation is the one that dominates every other representation in a fiber. Okay, so domination in this, you can think of it in the length spectrum setting, but there are finer conjecture where these metric tensors, there are harmonic maps associated with these representations. That's how non-abelian Hodges proved. But there are sort of finer conjectures regarding these domination of the metric tensors and energy densities.
The representations are into PSL and R?
Yeah, that's right. Yeah, so they form, yeah, so some special subset of the set of representations into PSLNC, and you can think of them as this image of the some kind of Hitchin section. Let me think of it. So the Hitchin section to this Hitchin fibration.
So basically that's the analog of the Fuchsian guys, right?
Yes, that's right. So in case of yes, thank you. So n equal to 2, so Hitchin representations are exactly the Fuchsian representations. Fuchsian for n equal to 2. But for higher n, I mean, yeah, there are more. You can also talk of Fuchsian representations in higher rank, which are sort of compositions of the Fuchsian representation with an irreducible representation of PSL2R into PSLNR. But those are special representations amongst the Hitchin ones. Okay, but for n equal to 2, the two coincide. So Fuchsian representations are exactly the Hitchin representations. Okay, anyway, so this is a sort of a general thing which hasn't been proved. It's open. I mean, Dai and Li have work which proves it for the n Fuchsian fibers, so the fibers which contain an n Fuchsian representations. As I just mentioned, n Fuchsian representations are special representations amongst the Hitchin ones, and this is a kind of a smaller subset, typically large codimension, but amongst them you have so for them Dai and Li had proved this conjecture, but otherwise it's completely open. And this talk I'll be focusing on yes.
Sorry, maybe I missed the definition. What's an n Fuchsian representation?
So sorry, I just mentioned it, but n Fuchsian is of Fuchsian, so pi 1s to PSL2R, and then followed by an irreducible representation that exists, a unique irreducible representation of PSL2R into PSLNR. And that's called N Fuchsian. So these give you special things amongst the Hitchin ones.
Nice.
Yeah.
Thanks.
All right. So this talk I'll be talking about punctured surfaces. So I'm going to look at surfaces with genus K, and at K punctures. K is at least one, I suppose. And I'll talk about a domination result for punctured surface into PSL2C first. This was some joint work with Wei Shu Su, and a domination result for PSLNC. This is joint work with a student of mine, Pabitra Burman. And these results will not use harmonic maps, or I won't talk about the sort of the analytical approach at all. We use a different point of view on the representation variety due to Fock-Goncharov. Okay, and so this, in fact, this argument we'll see will be somewhat more geometric, and for PSLNC, this will have some kind of algebraic flavor, some linear algebra flavor to it, and so it's completely different from the harmonic maps I was talking about. Okay, so let me first start with PSL2C representations, and talk of, and these are representations. Let me remind you of a punctured surface group now. So surface group of a punctured surface into PSL2C, and prove a domination and talk about the domination result there. So one of the things we need to do is we need to work with the relative representation varieties, and this is because of this fact that if you're allowed to increase lengths of the peripheral curves that bound the punctures, then even Fuchsian representations can be strictly dominated. And this is, again, a construction that goes back to Thurston, called Thurston's strip deformations. Maybe I'll just quickly say what that is. If you start with a hyperbolic surface with geodesic boundary, let's say, so this is a hyperbolic surface with geodesic boundary. So you can think of it as there's a Fuchsian representation for the punctured surface group now. You can attach a funnel to this boundary, and what a strip deformation is, so now it becomes a complete hyperbolic surface, although of infinite volume, infinite area here. So what you can, a strip deformation is something where you take an infinite strip, hyperbolic, infinite curve first, infinite geodesic, going out the funnel, and you insert a strip. Okay, so maybe I should use some other. So insert, you sort of, you glue in a hyperbolic strip here. So let me just say glue in an infinite hyperbolic strip. And what happens in the process is that lengths of curves on that original hyperbolic surface will all increase, because now the curve, every curve that passes, well, you have to sort of glue in through a set of filling strips. Let me just kind of, I've drawn this one strip here, but every time a curve passes through that strip, it's now longer in length than the original curve on that hyperbolic surface geodesic boundary, and the boundary length also has increased in the process. So this is just a sort of a kind of a vague idea, perhaps, but you can strictly dominate Fuchsian representations unless you kind of want to fix the boundary lengths. Okay, so, and this is what we are going to do.
So what exactly is a infinite hyperbolic strip? So it's, is it a thickened neighborhood of a geodesic, or?
No, it's.
I mean, what does it look in the universal cover?
So yeah, it's a region bounded between two non-parallel hyperbolic geodesics. So it's really something which is sort of flaring at both ends.
I see.
So that's what you glue in. Yeah. So you kind of, if you think of it in the universal cover, you're pushing, somehow you're sort of creating space by pushing the rest of the hyperbolic surface, to
so
aside.
It's going to be essentially determined by, so if you cut the hyperbolic plane along a bi-infinite geodesic,
right,
and then you're grafting in now a flaring hyperbolic strip.
That's right.
And the two geodesics on the two sides are glued to the two halves of the hyperbolic plane. Is that right?
Yeah. Yes.
And in the process, you get something that is isometric to the hyperbolic plane also.
Yeah, exactly.
Right?
Exactly.
Yeah. Okay.
Yeah, exactly.
Thanks.
Right. So anyway, so I'll mention strip deformations again, in fact, so if you restrict to relative representation variety, so this is where you fix the length of the peripheral curves. You have a tuple of k real numbers. It could be 0, for example, if you have a parabolic element, its length, translation length is 0. You can talk of this relative representation variety. Now, fixing the length in our case, PSL2C, is sort of amounts to fixing the conjugacy class of the, anyway, so I've expressed it this way, is fixing the length. Okay, so what happens here is that you can talk of domination as before, but the strict domination definition is slightly different, because now if you think about it, let me just draw sort of a cartoon of the surface. Here, the boundary length isn't changing. So you can't quite, if you include the peripheral loops, you can't quite have strict domination anymore in this relative representation variety. But you can talk of this almost strict domination. This is sort of a definition, sort of work of Sagman. I'll mention his work in a bit. And this is where there's this strict domination amongst curves contained in some compact set which is away from the boundary. So if you pick any compact set, there's some strict inequality. And one example is simple closed curves. So remember that. So simple closed curves. So here you kind of think of fixing some reference complete hyperbolic metric on your punctured surface, and so then that's where this definition kind of makes sense. So simple closed curves stay away from cusps. Okay? So that's sort of a fact, and there, so it sort of falls into this this set where you're taking a supremum, and in fact you have a strictly less than 1 here. And if you take, sort of, you allow self-intersections, etc., as long as, a curve doesn't sort of spiral a lot along the boundary, so that in that complete hyperbolic metric you chose, it's not spending a lot of time closer to the cusp, you will get this strict inequality. The strict bound, strict domination. All right. So this is sort of a slightly, this is fine-tuning the definition of strict domination in this relative case, and this is our theorem. This is this joint work with Wei Shu, Su, that for any representation PSL2C in a relative representation variety, there is a Fuchsian representation in the same relative representation variety that dominates rho. And if rho is not Fuchsian to begin with, then domination is almost strict in the sense that I just described. Okay, And a corollary of this, by the way, is there's some kind of Bayes constant for punctured surface groups as well, because there is a Bayes constant for hyperbolic surfaces with geodesic boundary, which was sort of proved in the same way I mentioned in the first slide. Let me just also mention that this theorem, as stated, wasn't quite new. Around the same time, this theorem was sort of implicit in the work of Nathaniel Sagman that I just mentioned in the previous slide. And even this corollary was proved by Junho Wang. But their results used harmonic maps. Okay, so Nathaniel, he kind of proved these analogs of the work of Donaldson and Labourie are mentioned in for these non-compact domains, these surfaces with punctures and so on. And so they not just Donaldson and Labourie, also the Wolf and Hitchin, and so they so they used harmonic maps. So our approach is different. So let me just describe that now. So our approach is using Fock-Goncharov coordinates in the moduli space of framed representations. So a framed representation is a pair of not just a representation of the surface group into PSL2C. Now it's all, when S would be a punctured surface, representation of the punctured surface group into PSL2C, but also a row equivariant map, which is the framing from the Fairy set to CP1. Okay, and what's the Fairy set? Well, it's a set of lifts of the punctures in the ideal boundary. Again, you can fix a reference hyperbolic metric finite volume if you like. I won't draw that, but here's the punctured surface, and you can think of so the lift of that of the punctures, which will be ideal points in the ideal boundary of S tilde, which you can now identify with H2 if you like. And so the Fairy set F infinity lives here. And this beta, this framing, is a row covariant map from the Fairy set, which has a natural action of pi1 of S on it to CP1. Okay. And this, so it's sort of, you have this extra framing, which is, you can think of as a choice of a point in CP1 associated with each of these punctures in the surface downstairs, if you like. Yes.
You actually get a map from the whole circle to get this in Amazon representations. You get this circle to, I mean, you get a continuous map from the circle also, right? I mean,
right. That's for a closed surface. Yes. Yeah. So that's right. So when you have a closed surface, then in fact you can also talk of an extension of this map to the whole circle, because then the points would be actually, if you define it, properly, then it's slightly different, the definitions. You don't have a puncture to talk of, can't talk of punctures, then you talk of lifts of geodesics on the surface, and so these geodesics will determine pairs of points in the boundary, and then but that forms a dense set on the pairs of points, and you can extend that map and get a map to a circle. Yes, that's right. So it's very much similar, but if you talk of punctured surfaces, you might not have an extension of the whole circle.
That was actually the point of my question. I mean, are there actually known examples where you do not have
no? So here I can take a Schottky representation, for instance, or something like that, right? So you need not. Absolutely. I mean, your set of points that you're defining it in might not be dense on the boundary, and this Fairy set might not be dense on the boundary.
Okay, that's very good. Thank you.
I mean, okay, sorry. Right. I mean, so the way I've stated here, I mean, these guys, with respect to that complete hyperbolic metric, yes, it is dense, but then it doesn't quite extend. If you take a Schottky representation rho, then it's something that's defined on F infinity, but not quite, can't quite.
Not on the, And basically, it's just that F infinity is an incompressible curve. So if it's a parabolic, you have a representation restricted to that. You don't have a map from the circle to the sphere completing that.
Yeah, that's right. Yes.
Absolutely.
So do you get a continuous map from the whole limit set?
No, not the circle. That's what he's saying. Yeah. So
not the whole circle, but so in this case, I see. Okay, subset of the circle.
Right.
Okay.
So I mean, so I guess, in this case, if I choose a reference complete hyperbolic metric, F infinity is dense in the circle. So I mean, the limit set would be the whole circle, but yeah. So the map I'm defining, the framing is only defined on F infinity. The Fairy set,
right?
Some countable set. Okay. So anyway, so this moduli space I mentioned of framed representations is the space of such pairs of a representation on the framing up to conjugation, and this just means that it's sort of a rho beta is the same as if you conjugate rho and you post compose beta by A, and then they're identified. So for each A in PSL2C. Okay, and Fock-Goncharov gave coordinates on this space of representations, which I'm denoting by rep with a hat on top of it. And this coordinates are defined with respect to an ideal triangulation. So let me go back to this picture. So I'm not going to attempt to draw an ideal triangulation on the surface downstairs, but there, you can have a triangulation where the vertices lie at the punctures. Okay, here there's just one puncture. In the universal cover, you will have a picture of the triangulation, a lift of the triangulation like this. Anyway, so something that lifts to the universal cover. And in the universal cover, for every edge, you can assign a complex number to, and this is the Fock-Goncharov coordinate for that edge. And this is just the cross ratio of the 4 points in CP1 that you get as the image of the framing of these ideal points, ideal vertices of the two triangles adjacent to the edge, as I've pictured here. Okay, so so this is an idea of what the Fock-Goncharov coordinate is, and they prove that this defines a birational isomorphism to see this complex torus. I mean, this is these defined coordinates on this space of framed representations. It's not quite defined everywhere because, for example, to define this cross ratio, you want these 4 points on CP1 to be distinct. So that's like a condition on your framing. So, but you can show it's defined on an open dense set of rep hat S, and these in fact birational coordinates for your moduli space of representations, framed representations. Okay, and moreover, if these cross ratios are real and positive, so Fock-Goncharov coordinates are real and positive, then what we just described is nothing but Teichmuller space. These are the shear coordinates for Teichmuller space. There's a plus here because it's sort of Teichmuller space where you allow the boundary lengths to kind of vary. And so there's an extra real parameter to every puncture. So you can think of some kind of decorated Teichmuller space. Okay, and so these are in other words, these representations, if you forget the framing, these representations are Fuchsian representations of the punctured surface group. Right, so this is Fock-Goncharov's work, and the idea of our proof is given a generic representation, we choose this framing and use its Fock-Goncharov coordinates to obtain a pleated plane in H3. Okay, so so let me just draw that picture again. So so in the universal cover, you have a triangulation. I'm going to just draw one triangle, let's say with ideal vertices ABC. So this is being mapped by beta. The framing maps these ideal points to 3 points on the boundary at infinity of H3, which you can think of as CP1. Okay, so here I'm thinking of hyperbolic 3 space as the interior of this ball, and in the interior of this ball you can have a totally geodesic ideal triangle with these points beta A, beta B, and beta C as the ideal points, and your map. I should have called it a psi now. So psi maps, these triangles, ideal triangles on the left to these totally geodesic ideal triangles on the right, which are sort of determined by the framing. And so anyway, so you get this some kind of surface that is totally geodesic in pieces, bent along these geodesic lines. So these totally geodesic triangles arranged in hyperbolic 3 space, and that's an example of a pleated plane. And by construction, this is a row equivariant map. Okay, and the key observation to give rise to this domination result is that if you straighten the pleated plane, it increases distances. So here's a sort of maybe a better picture. You have a pleated plane on the left, which is these totally geodesic ideal triangles bent along their edges. And when you straighten them out, you get something lying on an equatorial plane. And if you do that, then and you get this new map, which is an unpleated surface, if you like, unpleated plane, the mapping to the equatorial plane. And the key observation that I mentioned is that the distances increase when you do that, in hyperbolic 3 space. And this is how you get domination. And this new map rho 0, psi 0, is actually J equivariant with respect to some Fuchsian representation. This is the representation that dominates, the Fuchsian representation J. Okay, so this is an idea of our domination result. And notice that notice a couple of things. First, there was the second part of a theorem involving strict domination, and so almost strict. Let me just mention almost strict domination. For this, we need to do something more, and we need to do something with these strip deformations. So let me just not say much now, but let me just say you have to use strip deformations because okay, anyway, I won't mention much. So this is one thing. The other thing is that we had to start with a generic representation, remember, because we wanted Fock-Goncharov coordinates to work with, and that's not defined for every framed representation for the reasons I gave. But it turns out that it's defined for almost every representation, in particular representations, framed representations that are non-degenerate. So, here's a definition. This let me just mention that, because I've mentioned it here. So this is work of Allegretti and Bridgeland, who came up with the idea of this notion of degenerate and non-degenerate, which means not degenerate. So, and it turns out that these degenerate representations that I've defined here, you can think of it as some kind of analog of elementary representations for a closed surface group. This is a notion for a punctured surface group where you have, apart from the fact that, so these will be elementary, there will be either a global fixed point on CP1 or 2 points preserved by the image of the representation. Apart from that condition, you have sort of a slightly finer notion of every peripheral loop must fix these 2 points that are otherwise allowed to be swapped by elements of the image. Anyway, so there is this notion of a degenerate representation, and Allegretti Bridgeland showed that these are exactly the ones that are missed by, that don't have well-defined Fock-Goncharov coordinates. And we have a different argument for that. And that argument, in fact, uses harmonic maps, and we rely on Sagman's work. Let me just mention one example of such a representation very briefly. So for example, if you have an elementary representation or degenerate representation mapping to PSL2C that fixes a geodesic, they're all loxodromics, hyperbolics, fixing sort of 2 points and the geodesic axis between them. You can think of this representation as a representation to R, if you like, because it's acting on this geodesic. So you can think of it as conjugate to a diagonal representation. So these representations are going to be degenerate, and for this we had to rely on harmonic maps again, but maybe there's a sort of a different approach without harmonic maps with these two. In fact, there is one by Guritod, Cassel, and Wolf, whom I mentioned. They proved as I mentioned earlier, they proved a domination result for PSL2R representations, and this is also a special case of in that paper. And anyway, so there's but perhaps there's even simpler proof which can be found. But anyway, I don't know. So that's the idea of the proof of PSL 2C. Running out of time, but let me at last, sort of go on to PSLNC representations. And so the first thing I need to do is talk about the row length, the length of curves of such representations. So this is how I define it. It's the log of the ratio of the smallest and largest eigenvalues and modulus of rho of gamma. And this coincides with the definition of length in n equal to 2, by the way, which is, and this is a notion of lengths of curves, which is used for Hitchin representations, which is also called the Hilbert length. This is exactly, so Hitchin representations to PSL3R, these are also, turns out that these are convex projective structures which carry a Hilbert metric, and this length I've defined is actually the Hilbert length of the curve, and it's also called in some part of the literature the width of the curve gamma. And there are other notions of length. You can talk of the spectral log of the spectral radius, which is the largest eigenvalue, and this also gives the notion of length of curves. And it's also, you can also talk of the translation length in the symmetric space for PSLNC. And that's a notion of length that uses all the eigenvalues. So, so these are notions we won't talk about this talk, but hopefully in another one. And you can also talk of the moduli space of framed PSLNC representations. And this is what I denote by rep n. And this time, from the fairy set, you have the row equivariant maps to the space of complete flags in Cn. So this is like a, you can think of this increasing subspaces in Cn. And this is some kind of boundary of the symmetric space, right? I don't know, this may be called probably equivalent to the Furstenberg boundary. Anyway, it's G mod B. In this case, it's G is PSLNC, and B is the Borel subgroup of upper triangular matrices. Okay.
Probably strictly upper triangular?
No, it includes the diagonal. Yeah.
So what I mean is, don't you want something like G mod P or B? That's what I'm getting confused for, because
so the minimal parabolic. Let me just put it this way.
The minimal
okay, so the minimal
yeah.
parabolic.
Yeah.
Okay, so so there are Fock-Goncharov coordinates for this space as well. So this is a Fock-Goncharov coordinates on well, I was calling it rep n hat of S. And these are given by these what are called triple ratios of flags, triples of flags, and edge ratios, quadruples of flags, which are parameters associated with these ideal triangles. Now you might have parameters not just along the edges, like I've sort of mentioned here, but also in the interior of the ideal triangles, which are sort of different from the case of n equal to 2. And once again, Fock-Goncharov showed that there's this birational isomorphism from rep n to some sort of complex torus. So this is, again, with respect to some ideal triangulation, and there's some number of parameters which I'm not bothering to count at the moment. So, so there is this parameterization of this moduli space. And in fact, these positive real points, just like before, are Hitchin representations in this context. So I should mention that there's, Hitchin's work used Higgs bundles and this analytical input. There is a version of that for punctured surfaces involving parabolic Higgs bundles, which I guess the references Biswas and Indranil's paper, Aris Gastesi and Govindarajan. And anyway, I'm kind of running out of space here, but the fact that these positive real points are Hitchin representations is also sort of mentioned in these works, Labourie and McShane and Canary, Zhang and Zimmer. These are cases where the boundary monodromy, the peripheral curves have different properties here that's sort of real and split, so they're sort of diagonalizable with real eigenvalues. And here it's unipotent. And in these cases, these some kind of relative Hitchin representations have been studied and identified with these positive representations in the sense of Fock and Goncharov. Okay, and here's a theorem. This is this, maybe I should also mention this is sort of ongoing work of this PhD student of mine, Pavitra Burman, which says that for a generic representation to PSLNC, there exists a Hitchin representation to PSLNR that dominates rho. Okay, so you have this domination in the length spectrum, this rho length that I've defined before. And in this domination, you keep the peripheral loops the same length. So in the cases of, the cases I mentioned, sort of in the cases of loxodromic or unipotent, boundary conditions, they are in the same relative representation variety. So where the relative representation variety now sort of fixes the conjugacy classes of these elements, there's peripheral elements, because this is something that is kind of also studied when one studies representation varieties of punctured surface groups. Okay, and let me mention that there is an almost strict domination statement that one should be able to make, but in general, it's not. If the way I've stated like this is not quite interesting, because it's possible, unlike the n equal to 2 case, it's possible to strictly dominate a Hitchin representation by another, so even of a closed surface group. And this was, let me just mention this sort of work of Pengren Zhang. And so anyway, it's sort of also a consequence of the stuff I'll talk about, the proof of what we do, okay? And also let me mention that our result says generic because there is, we don't know a good characterization of the non-generic representations, just like there was for the n equal to 2 case, okay? Anyway, do I have a couple more minutes, or I guess I've over time now? So maybe
please say a few words about the general.
Okay, I'll just give an idea of the proof. And one of the difficulties, let me just say, is that there's no analog of a pleated plane in the symmetric space X. Okay, so there's no good analog that I know of, at least. But what we use is more of the work of Fock and Goncharov. And Fock and Goncharov showed that in fact, this monodromy of loops, you can compute as a product of matrices that are determined by the Fock-Goncharov parameters of the edges and triangles, ideal triangles that are crossed by a lift of the loop in the universal cover. Okay, and so what the key observation was is the fact that these matrices are of a very special form. This is something that Fock and Goncharov kind of they defined how to get these matrices. And our observation was these products of matrices of an edge matrix and a triangle parameter matrix are actually weight matrices of planar networks. So let me define what they are. That's the sort of the last new thing I mentioned in this talk. So this planar network is some kind of directed graph on the plane with n sources and n sinks. So I've drawn one here. So here the directions, I've not put the arrows, but you can think of them as sort of being directed from left to right and from bottom to top. Okay, all these edges in the picture. And to such a directed planar graph, you can associate a matrix with, which is the sum of weights of paths from, from the ith source here to the jth source here. And a weight of path is the products of the weights of edges that you encounter when you do it. Okay, so this is sort of, it's something like, sort of you look at all sets of paths, there must be some, I feel there's some probability involved here. Anyway, I won't get into that now. But, so if this, let me call this planar graph gamma, then the weight matrix of this guy, for example, I don't have time to work it out, so let me just note down what I had calculated. So it's something like this. Okay, so for example, I mean, if you look at sort of all paths from sort of 1 to 2, so you can either go this way, which will pick up a weight y, which is one of these terms here, or you can do yz. So that's the other term here. Okay, so this is a weight matrix of a planar network. And a fact that I learned from this article of Fomin and Zelevinsky is that, if the edge weights are all real and positive instead of complex numbers, then this weight matrix is totally non-negative. Which means that all the minors are non-negative. And here's another fact that's more elementary. So if we concatenate two weight matrices, two planar networks, then their weight matrices sort of multiply. Okay, so you can sort of place them side by side and connect up, and you get a weight matrix of the larger planar network. And these are what we use together with this key lemma. This is the sort of the key, the heart of the argument, that if you replace weights which are complex by their modulus, then you get real and positive weights. Then the spectral radii of the matrices, of the weight matrices increase. Okay, so the weight matrix of this new weight planar network is greater. So this is sort of the heart of this our domination result. I won't get into the proof of this, which is fairly elementary.
So this lemma plays the role of this lemma plays the role of straightening of pleated surfaces.
Yeah, that's right. Yeah, that's right. Yeah, so there's no geometric picture now, but at least there's this algebraic result that allows us to do get to this domination result. And the proof is basically short. It's one page using some characterization of spectral radius for totally positive matrices that's well known to linear algebraists. And let us sort of conclude by sort of mentioning this almost almost strict domination result that might be possible. So going back to this picture that we had of the Hitchin fibration, there is a picture like that here as well, because you can divide these complex Fock-Goncharov parameters in the case of the n equal to 2, the shear and bend parameters. And these, if you fix the shear parameters, the bend parameters determine this torus in this picture. And it might be possible to show that, that in fact the entropy let me first mention that our techniques show that a generic element in this tori are almost strictly dominated by the Hitchin representation. So very roughly speaking, so whenever your curve crosses one of these triangles with complex parameters, and so that when you kind of replace them with the modulus, there's some kind of strict triangle inequality in some sense. So then you would have some kind of, you pick up some sort of actual sort of strict inequality, and you'll get this almost strict domination. And so you have for generic elements, you have some kind of almost strict domination, and it should be possible to show that the entropy of every element is in fact strictly greater. So something finer, because the entropy, the way I defined it, you don't quite need a length spectrum bound on all curves. You need it for most of them in some sense, and so anyway, this is another thing that we will be doing, and so that's why it's ongoing work. And there are other directions. For example, you can extend the case of closed surfaces, or there are other domination results, and we can prove for closed surfaces that are known, and one can try to prove relative versions of these. So these are sort of more directions that we can go to. So I'm really sorry for going over time, but I'll stop here now.
Okay, let's thank the speaker for this very interesting talk. So we had many questions during the talk. Are there further questions?
Yeah, sorry, because it's sort of straining people's patience. But yeah, so the thing is, what exactly is the analog of the strip deformation? Because you still have, say, basically, you're trying to split a pair of points code flats probably in the flag in the space of flags. So is there a geometric interpretation of inserting this
so unfortunately not. So the strict deformation, so we needed, for n equal to 2, we needed the strip deformation part to get to that strict domination result.
Yeah.
So in this case, the deformations that Tengren-Zhang introduced wasn't strip deformations. So I don't think there is an analog of a strip deformation for higher rank, for Hitchin representations and greater than 2. But for Tengren-Zhang, what he used are, he proved it for closed surfaces, but, one can prove it for, surfaces with boundary as well. But he uses what are called Goldman parameters, I guess. He also has a version for Hitchin representations, but for n equal to 3, these are parameters on pairs of pans, and he showed that if you deform them in a certain way, you scale them, you increase them in a certain way, then the lengths of curves will increase eventually. They'll grow. So that is how this increasing lengths of curves was done in this context. But that is different from strip deformations, because I think the thing is, the strip deformations, in this setting, for example, n equal to 3, which are convex projective structures, if you define some kind of deformation like this naively for a convex projective structure, if you insert some strip in RP2 or something like that, then you might break convexity of the domain. So somehow something that was sort of automatic in the n equal to 2 case, it's not quite the same for higher rank. So there is no analog of a strip deformation, but there is some substitute, which is this work of Tengren.
So the thing is, this is about deforming pairs of pans, but is there, there's sort of a standard yoga for translating pair of pans decompositions to ideal triangle decompositions. Is there a transfer, basically, because you're talking about Fock-Goncharov coordinates, which is sort of more suitable?
That's right. I think so. Yeah, I think so. So in fact, that's one of the things that I mentioned here. At least for Hitchin representations, there is this. There is this notion of parameters for idea for closed surfaces, this work of Bonahon and Dreyer. So their stuff is some kind of generalization of the Fock-Goncharov parameters, or some kind of version of Fock-Goncharov parameters for this case, where you might have these spiraling leaves, ideal triangulations here. And I think, so Tengren has a paper which involves those to prove his result on kind of increasing lengths of curves. I mean, he showed that the entropy of Hitchin representations might go to 0. That was his sort of his thing. So somehow strict domination is not as interesting. Just if I just state it like that, but it's more interesting if we talk of these fibers where sort of.
I see.
Yeah. So if you go, in other words, I mean, I have this plane of Hitchin representations. If I go in some direction, I can find Hitchin representations as entropy going to 0, length spectrum dominating of any one of these guys. But I think the more interesting question is, whether the same in the same fiber does the Hitchin representation dominate that. And so that's sort of the kind of the correct thing to.
Right. Okay, great. Thank you. Very, very lovely talk. Yeah.
Okay, thank you.
Okay. Seems like there are no further questions. In that case, yeah, let's thank Subhojoy one more time.
Thank you very much.
Thanks, Subhojoy. Could you please send me the slides? I'll put the recording as well as the slide on the webpage.
Okay, sure. I'll do that.
Yeah.
Yeah, thanks.
Thank you. Thanks.
Okay, thank you.
Bye.
Bye. See you.